continue. Yeah. All right. So let me start. Now I need chalk. So there. Now, what we ended up with yesterday is we had written down the mode expansions of the free boson. I'm not going to write them down again because life is short. And I had derived the commutation relations of this chiral field. Which are a little bit unusual because they involve the sine function. And then if you just look at the mode expansion, you can immediately see that in the conventions that I'm using, the left and right chiral fields commute. Yeah, and other people use other conventions, so you always have to check for the details. Now, having the mode expansion, we can compute correlation functions. And what these look like, Hubert has already told you, but I'm basically just going to tell you how to work them out in a ab initio fashion, if you wish. So let's look at the ground state two-point function of this chiral field, vertex operator of the chiral field, e to the I beta phi right of x minus prime. So let's try to work out what this is. Okay, and Hubert had already written yesterday, it's some kind of power law for certain values of alpha and beta, and I'm just going to explain to you now where it comes from. So the key for working this out from the mode expansion is what's called the Baker-Campbell Hausdorff formula. And that basically is a formula that tells you how exponentials of operators multiply. And in general, if you have the exponential of two operators, you multiply them, you get something which is very complicated. And these people basically worked out what you get. Now we need a very simplified form of this Baker-Campbell-Hausdorff formula, which applies to cases when the commutator of A with B is non-zero, but proportional to the identity. Okay, if the commutator is 0, then e to the A, e to the B is just e to the A plus B, so it's trivial. Now, if the commutator is proportional to the identity, you pick up an extra piece, which is just proportional to the commutator. Yeah, so it's an extra factor, but it's a non-trivial factor. Okay, so if you haven't seen this before, so in this case, you can prove this formula very easily just by expanding everything, and you prove it order by order. Okay, so I'm going to use that now to work out the commutator I like. So I work out the correlator I want to know. Okay, so A is I alpha phi right of x minus, B is I beta phi right of x minus prime. So then what I get is e to the I alpha phi right of x minus, e to the I beta phi right x minus prime. That is e to the I, just the sum, alpha phi right of x minus plus I beta phi right of x minus prime. Okay, so that piece we still have to work out. And then I get this extra factor, and this extra factor involves just the commutator of the chiral fields. So that gives me an extra phase factor, which is minus I alpha beta divided by 8 times the sine x minus minus x minus prime. Okay? Now, what remains to be done is to work out this expectation value. So it's the expectation value of an exponential of the sum of two chiral fields. Now, there will be two pieces to this. So one piece is the piece that comes from the zero modes that we spent some time on yesterday. And the other piece is the one that comes from the finite momentum modes. And so now I will compute them in turn. So the zero mode part looks like so. So let me call this gamma. The zero mode part looks like this. E to the I alpha plus beta q minus I divided by 2L p alpha x minus plus, no, sorry, minus beta x minus prime. Yeah, okay. That's just plugging in the mode expansion. Okay, so now this is a problem just involving a single harmonic oscillator. Yeah, and the way we can work this out, now we can use this Baker-Campbell-Hausdorff formula in the reverse. So we have something which is like e to the a plus b. We can pull it apart into something e to the a times e to the b times e to the minus 1/2 the commutator. Yeah, and the commutator q with p is just I, so this is some function I don't care. But after pulling it apart, I get something like this. E to the I alpha plus beta q e to the minus I divided by 2L alpha x minus minus beta x minus prime p 0 times e to the minus 1/2 commutator. Okay, so we don't care about this part because this one will be very simple now. The point is, this, by what I had shown you yesterday, is actually an eigenstate of P. Yeah, but with an eigenvalue that is different from the eigenvalue of the ground state. Okay, so in other words, that state, it's an eigenstate of this operator, but it's orthogonal to 0. So in other words, this vanishes, and the only way I can avoid this is if alpha plus beta is precisely equal to 0, because then I don't have this part. And I don't, yeah. Okay, so when alpha equals minus beta, I don't have this. And then you get the ground state expectation value of e to the IP, and this is just 1. Yeah, so in other words, this is just Kronecker delta alpha minus beta. So in other words, because of the 0 modes, this expectation value, or this 2-point function, vanishes unless beta is minus alpha. Okay? And it comes from the 0 modes. Now, the other part I have to work out is the finite momentum modes. When alpha, no, so I discussed this, but I went a little bit fast. I go back to this formula, and I said alpha equals minus beta, then this is gone. I get e to the I p times something, but I don't care because the expectation value of p vanishes. So it's just 1 if alpha is minus beta. Okay? So I'm just going a little bit fast because I'm way behind schedule. Okay, let's do finite momentum modes. So there we use, okay, so the finite momentum modes, they all commute with one another, so it's just a bunch of harmonic oscillators. So we can just work out what happens with a single mode, with one of these K modes, and then all of them will work in the same way. So I can do it mode by mode, and for a single mode, I need to know expectation values like this. So I have something like gamma beta n plus delta beta n dagger. Yeah, so these are the kinds of expectation values I get for the modes that appear here in this sum. It's linear in beta and linear in beta dagger. Okay, and this we now know how to do. We use our favorite Baker-Campbell-Hausdorff formula, and this is just e to the gamma delta over 2, just this commutator. Okay, and now you use this, yeah, so then this becomes basically the exponential of the sum of some stuff, yeah, and then what you do is you just carry out the sum, it gives you a logarithm, and then you have the exponential of some logarithm which gives you some power law, and so after the dust settles, so this is again an exercise, but you know now how to do this. You find that gamma is equal to delta alpha minus beta. So this is what we get from the zero modes. And then now we have a piece that again involves our cutoff, the one I introduced yesterday, the smooth momentum cutoff. Okay, because when you look at the sum over the modes, you again have a sum over all the modes, and you have to cut off the large momentum modes, which involves this regulator epsilon, and then from the e to the actually, so that's not what I want to write. So what I want to write is just this straight away. So I want to include this factor, e to the I alpha phi right of x minus, e to the minus I alpha phi right of x minus prime is equal to two pi I epsilon divided by 2 sine pi over L x minus minus x minus prime, and this whole thing to the alpha squared over 4 pi. Okay, and if I have the beta here, we would have a delta alpha minus beta. Whew, okay, so this is the answer. I kind of sketched for you how you get it. Now, where am I? Okay, so this depends on this ultraviolet cutoff, epsilon. And so the formula looks similar to the one Hubert had written for you yesterday. It's not exactly the same, but we'll make it look a little bit more similar in a second. So depends on regulator UV regulator epsilon. Okay, and for me this UV regulator, it's a dimensionless quantity, so that's the way I had introduced it, just e to the minus 2 pi epsilon. Yeah, so we can relate this to dimension full, well, let's see, lattice spacing A naught. This is what Hubert had used as the ultraviolet regulator, just a lattice spacing. And this is dimensionless, this is dimension full, so I should set epsilon is something like A naught divided by the length of the system. Yeah, and these are the kinds of factors Hubert had written for you yesterday. Okay? Bear with me. Bear with me. Bear with me. So give me 10 minutes. Yeah. So at the moment, what I have done is I have worked with periodic boundary conditions. Yeah. So my spatial coordinate is a ring. Okay. So therefore, my answer better be periodic. Otherwise, I would have made a mistake. So it is periodic. So I'm good. Yeah. Good. Yeah. And so what don't you like? Well, okay, but so the way this came about is literally just from the mode expansion, so to speak. Yeah, because okay, so the chiral fields, they don't depend just on x and t separately. They depend on x minus vt and x plus vt. Okay, so now, if you wish, just take these equations and set t equal to 0. So look at equal time correlation functions. So then this just would depend on the spatial coordinate. Yeah, but the mode expansion doesn't make a distinction between x and x minus vt, x plus vt, because only the combination enters. The compactification of the field is super important because all the zero mode story comes from the compactification of the field. So the fact that this 2-point function is 0 unless alpha is equal to minus beta, that came from the zero modes. Yeah, and the zero modes encode all the information about the compactness of the field. Yeah. So the compactness is very, very important. Okay. Now, okay, so we can define, so we can introduce a normal ordering. Oops, no, this I didn't want to do. So I define a normal ordered vertex operator like so. E to the I alpha q minus I alpha p x minus divided by L. So here I don't do anything to the zero mode part of the vertex operator, but then I do normal order the finite momentum modes. So here I put e to the I alpha n positive beta n dagger square root 4 pi n e to the minus I k n x minus. And then here I put the annihilation operators to the right. I alpha n positive beta n square root 4 pi n e to the I k n x minus. Okay, so that's a definition. Yeah, so I define that as the normal ordered vertex operator. And using Baker-Campbell-Hausdorff, we can relate this again to the not normal ordered vertex operator, yeah, by just using the Baker-Campbell-Hausdorff on these two factors involving the modes. And this gives us precisely this divergent piece times e to the I alpha. Yeah, and so this is also one of the formulas Hubert had written for you yesterday. Okay, and so finally, so these vertex operators, they multiply like e to the I phi r of x, e to the I phi r alpha beta of y is e to the I alpha phi right of x plus e to I beta phi right of y, normal ordered, and then you get an extra factor, minus 2i sine pi over L x minus y. Something like this. Okay. We have this. Okay, and now I want to do one final thing. And then we finish with this free boson. So far, I've been trying, I was very careful, so I had a ring of length L with periodic boundary conditions, and I kept careful track of these periodic boundary conditions, which is why I had this sign and so on and so forth. So in practice, we are not really interested in the finite volume. So we are interested in things like x minus y much less than L. Yeah. And in that case, things simplify, and we get stuff like this. I alpha phi right of x e to the minus I alpha phi right of y equals I epsilon L divided by x minus y alpha squared over 4 pi. Yeah, and this epsilon L is written over there, so this is lattice spacing. And this is really the kind of formula I want to use in the following. So this is where I wanted to go with this review of the free boson. Okay, and that's all I'm going to say about the free boson for now. So later we will basically use these kinds of formulas. Yeah, but for the so when we bosonize these Fermi models, so we always will do it having in mind that x and y are very small compared to the length of the lattice. Okay, so that's all I'm going to say about this, and now I'm going to change direction. So any comments, questions about this? No? Okay. So what I want to do next is, so now I reviewed for you this free theory, and in the end of the day, it's just a free theory. However, it has some unusual properties which come from the compactness of the field. So these zero modes cause some complications. That's number one. And number two, compared to the free boson theory that one learns in the first quantum field theory course, well, okay, so the important operators, the operators of interest, are these vertex operators. Okay, but now we understand basically how to deal with them, so all is good. So now the next thing I want to do is I want to discuss a little bit, if I don't have just a free boson theory, like the one we just described, but if I perturb it by various types of operators, okay? Because this is the situation we encounter when we carry on. So, and the way to understand these perturbations is in terms of renormalization groups. So, what I'm going to do now for you is to discuss a little bit the Wilsonian version of the renormalization group for a perturbed free boson. And in particular, what I will discuss is this Kosterlitz-Thouless transition. So the Lagrangian of the compact boson is just integral dx 1 over 2v dt phi squared minus v over 2 dx phi squared. So something like this. Okay. And to simplify things, well, okay. Now what we want to do is work in Euclidean time, in Euclidean space, rather than Minkowski. So what we do is we introduce this imaginary time. Tau is IT. Okay, and then we also change variables to remove this velocity. So we introduce a variable y, which is v times tau. And once I do that, the action in Euclidean space that I get by doing this looks like this. It's 1/2 integral dx squared. So integral dx squared is now just dx dy. And here I have grad phi squared. Okay? So here the action just would be integral dt over the Lagrangian, but if I do this change of variables, yeah, so I get this. Okay, and basically I do this because the manipulations I'm going to show you now are less cumbersome in this Euclidean formalism. It's a little bit easier. Okay, so now consider a perturbation of the form integral d squared x 1/2 grad squared. So that is the free part. But now I want to add lambda cosine beta phi. Okay, so for now, this is just a perturbation of this free theory. Later, next lecture or whatever, we will see when we study this interacting fermion theory. So this is precisely the kind of models that we need to consider. So you will see why we now discuss perturbation of this form. Okay, and what we want to understand is is this perturbation important or not important? Yeah, in the renormalization group sense. Yeah, and the way we do this is we look at the partition function. Yeah, which I write as a path integral over this Euclidean action, like so. And here I have the free part and then the perturbation. So I'm assuming here that you all have seen a path integral before. I mean, is that actually a valid assumption? So who has seen a path integral before? Yay, okay, good. So I don't have to, because, yeah, okay. Now, correlators. Would be objects like this, phi of x, phi of 0, 1 over z, integral, path integral d phi, phi of x, phi of 0, e to the minus se of phi, etc. Okay. Okay, so now the idea of Wilsonian RG. Okay, so there are many ways of doing the RG I should have mentioned. So one way of doing is using this operator product expansion that Hubert mentioned yesterday, but I purposefully wanted to go down this Wilsonian path because it's very intuitive. So you really can see in the simplest possible way how it works. And the price of it, it's a little bit more cumbersome. Okay, so what you have to do is first we need a cutoff to make the theory well defined. So we define a cutoff dependent field, which would be the integral over the momentum modes, if you wish, but now I introduce a sharp cutoff, so I take these momentum modes only inside a sphere of radius lambda. Yeah. And so what I had done yesterday in Minkowski space, I had this smooth cutoff, yeah, where I simply had suppressed the high momentum modes more and more. So here we work with a sharp cutoff for the time being, and again, this is because from a pedagogical point of view, it's the easiest way to proceed for the time being. Where am I? Here. Okay, now the idea of Wilsonian RG is integrate out the degrees of freedom in the vicinity of the cutoff and see how this affects the low energy part of the theory. Yeah, so it's very intuitive. So you basically get rid of the high momentum degrees of freedom. These are short distance degree of freedom. Integrate them out, but okay, so the interaction, so these short distance degrees of freedom interact in some ways with the long distance ones. So if you get rid of the short distance one, you renormalize the long wavelength degrees of freedom, and by doing this, you can work out how that comes about. So what we will do now is we will change the cutoff from lambda to lambda prime, which is less than lambda. Okay, and okay, because it's a sharp cutoff, this can be implemented very easily. So we can decompose the field as a low energy part so this we call phi lambda prime. And then the high energy part, which is just the integral over the momentum modes between the old and the new cutoff. Yeah, and this becomes h of x. Yeah, so the field is just the sum of two terms. Yeah, so it's the low energy degrees of freedom, which are the small momentum modes, if you wish, and then the fast degrees of freedom, which are the high energy modes. Okay, now the idea is we want to carry out the path integral over this field and see how that changes the remaining action for the slow degrees of freedom. If I can find it, so here. Okay, so let's just write this down. So phi lambda prime are the slow and h are the fast degrees of freedom. Okay, now let's look at the action first. So the action depends on phi lambda, and it has a free part and the interaction part. So far I haven't done anything. Yeah. So now I start doing things. Here, this is just the Gaussian action. Yeah. So 1/2 grad phi squared, and this one just becomes the sum of the actions, Gaussian actions for phi lambda prime and h. Just to make sure that you're still following. So why is this? Yeah, okay, in a sense, yes, but if you have to prove it, how do you prove it? Hmm? You just look at the Fourier components, right? Because it's diagonal in Fourier space. Hmm? Sorry? No, but so this is just a property of the free action. So I'm not dealing with this yet. So this simply comes from the fact that in terms of the momentum modes, the action is diagonal. Yeah, so you have basically phi k squared. Yeah, so there are no cross terms between the slow momentum modes and the fast momentum modes. So this is where this comes from. Okay. Now, yeah. So we are here. Now I'm going to work out what the partition function is. Oops. Okay, so I just finish this and then we take a break. Okay. Now, so z lambda, the partition function, becomes d phi lambda prime integral e to the minus s naught phi lambda prime. And then here I get the path integral over the fast modes, dh. And then I have e to the minus s naught, s e naught, this is called, of h minus lambda s int phi lambda prime plus h. Okay, that's just plugging it in. Now, this we like, so this will remain untouched. What I want to do now is I want to somehow carry out this path integral here. Okay, but I can't really do that, right? Because it's very complicated because this piece here is in the exponent. So what I will do now is I will use that lambda as a small parameter. So we will view this perturbatively. And we will look at the first couple of terms in lambda. Okay, so we'll introduce a notation. So this is proportional to e to the minus lambda s int phi lambda prime plus h averaged with respect to the fast degrees of freedom. And I write here proportional because I have thrown out, so it would be equal to ZH times this. Okay, but this, as far as my path integral is concerned, is just an overall constant, which we don't care about anyway, right? Because what we care about is the lambda dependence here of this partition function. Okay. Now what I do is I expand this in a power series. No, before I do that, I can write the following. So this gives an additional contribution to the action. So SE of phi lambda becomes SE0 phi lambda prime. And then the full answer here, I would have the logarithm of e to the minus lambda s int phi lambda prime plus h. Okay, so that would be the full answer, the full non-perturbative answer. But obviously I cannot compute this object here completely. So what I will do instead is expand this expectation value in a power series. So log e to the minus lambda s int, I say, is something like log 1 minus lambda s int phi lambda prime plus h, and then plus lambda squared over 2 s int squared plus dot dot dot. Just expanding the exponential. And now it's the log of 1 plus something small. Now I use that lambda as a small parameter. Yeah. And then I get, this becomes minus lambda s int phi lambda prime plus h plus lambda squared over 2 s int squared phi lambda prime plus h, and then we have another piece here minus s int squared plus order lambda cubed. Okay? And what I'm going to do after the break is I will evaluate the first couple of orders in lambda. I will evaluate this, and I will evaluate this, and this will tell us then how the action changes if we integrate out these fast degrees of freedom. Okay, so let's take the break now. Okay, so this we put there. Okay, so now we are here. All right, so let's continue. So to first order, I need to work out what is the average with regard to these fast degrees of freedom of the interaction term. Yeah, and let's just write this down. It would be integral d squared x, and then here we would have the average of cosine beta, and here we have phi lambda prime plus h. Okay, and then this becomes 1/2. Here we get e to the I beta phi lambda prime, and then we get here the expectation value of e to the I beta h with h. And then here we have plus complex conjugate or Hermitian conjugate. All right. So now I need to work out what is this expectation value here. So this is e to the I beta h of x. Well, okay, so if you want to do it fully explicitly, okay, let me do that. So it's 1 plus I beta h of x, h minus beta squared over 2, h squared of x, h plus dot dot dot. Oops. Now this is just 0 because it's odd. Yeah, but yeah. Sorry. okay, so this one is just 0 because it's odd, yeah, and the free action is even in H. So the first contribution is this one here, yeah, and so this is 1 minus beta squared over 2, and then we can write this out explicitly. This is now integral lambda prime less than k less than lambda. Yeah, so my momentum shell, this is where H lives. Integral t squared k over 2 pi squared. And here we get h of k, h of minus k, h, yeah, and this is just 1 over k absolute value squared, yeah, because the action is grad squared, yeah, it gives you a k squared, so the propagator is 1 over k squared, yeah, so we have this, and this is 1 minus beta squared over 4 pi. Here I just do the integral now. It gives me something which I call dl plus order dl squared, where dl I call log lambda over lambda prime, which is the same as log 1 plus lambda minus lambda prime over lambda prime, which is the same as, approximately the same as lambda minus lambda prime over lambda prime. Okay, so this, you just do this integral in polar coordinates, yeah, so then it's elementary integral which gives you the log, yeah, which I call dl. Okay, so this is nice. So this tells us now how integrating out these fast degrees of freedom modifies the action for the slow degrees of freedom. So this is SE0 phi of lambda prime. And then here we pick up this additional piece, lambda 1 minus beta squared over 4 pi dl. And here we get d squared x cosine beta phi prime. Okay, so that is the first result. And what we see is that integrating out this momentum shell has renormalized this coupling constant here. Okay? Now, to do the RG, so to complete the RG step, we must rescale the momenta and positions to recover the original cutoff. So we have to take k goes to lambda over lambda prime k, and x scales in the reverse way is lambda prime over lambda x. And this gives us then the final answer, SF of lambda, phi lambda, is SE0 phi lambda plus, here we just get an extra piece, 1 plus 2 minus beta squared over 4 pi dl integral d squared x cosine beta phi lambda. Okay, so that is the result of the first order calculation. Just a brief comment. So under this rescaling, the free part of the action doesn't change because it's scale invariant. But here the interaction part, you pick up this additional contribution of 2 times dl times lambda times the cosine beta phi from the rescaling of the dx. Okay. So now, it's a relatively simple calculation. It's a relatively simple calculation, but it tells us, yeah. Not really. So what I have done here, I have thrown away all these subtleties. So I was very careful with the free boson in the previous lecture for reasons you'll see in the next lecture, because I wanted the finite size spectrum in its full glory with periodic boundary conditions, because I'm going to use this to motivate the equivalence of the free bosons to a free boson or to a free fermionic theory. Okay, so we will need this later. So here, we don't need it to. No. So here, all I have done is I have written cosine beta whatever here is e to the I beta whatever is here plus e to the minus I beta. As far as the expectation value in H is concerned, this doesn't feel it. It's different degrees of freedom. It's the slow degrees of freedom. So the average over H only affects the H field. Yeah? And so therefore, this is just equal to this. And the and this is what I have. This is what I have here. Yeah. So I have not cheated. Everything is fully here. I see you. So, but all I need here. So forget about there are no zero modes. Nothing here. All I do here is I put a sharp momentum cutoff in my theory. And then I lower that cutoff and I integrate out the momentum shell. And for that calculation, at least to leading order, all of these subtleties that we had previously, they're not there. I don't need them. Yeah, so this is a much more elementary calculation. Only the high momentum modes matter, you see? Because I take the average with respect to the high momentum modes, which is why I don't have to worry about zero modes and all these things. Okay? I'm not sure I quite understand the question. So what I have done here, I have done the full calculation in order lambda. So all of the contributions to order lambda are accounted for. So little lambda, I mean, so this one. So to leading order in perturbation theory, so to speak, I took everything, yeah? And the only other expansion I used implicitly, and maybe this is what you're asking, I use that dl is very small. So I integrate out a small momentum shell. So I throw away terms which are dl squared, but this is fine. Yeah. So to order lambda, everything is accounted for, and it's still fairly simple. You'll see the kind of complications that you maybe have in mind to order lambda squared. Yeah. So they're the full glory or whatever you want to call it of RG shows itself. So I'm going to sketch this in a moment. Okay? So, but let's first stick with this result, because the calculation was fairly simple, but it gives us this very far-reaching result, actually. So we can learn quite a lot from this. So let's call this renormalized coupling, we call it lambda prime, little lambda prime. Okay, so what this RG step does, it renormalizes the coupling constant. So my coupling constant becomes, if you wish, scale dependent. And now using that this dl is very small, we can work out what the lambda dl is. This is just lambda of L times 2 minus beta squared over 4 pi. And the initial conditions are lambda of 0 is just lambda. Okay, so this is what we showed explicitly. So now this has very far-reaching ramifications. Okay, so now there are two regimes. If beta squared is in fact larger than 8 pi, that's the first regime, then lambda of L eventually goes to 0. Yeah, so as I integrate out more and more high energy degrees of freedom, the coupling constant becomes smaller and smaller and smaller and smaller. Yeah, and this is very nice as L increases under RG flow. So this tells us that cosine beta phi is an irrelevant perturbation. Okay, so if I add such a perturbation, cosine beta phi, to this free boson theory, but beta squared is larger than 8 pi, the low energy physics is actually not affected by this perturbation. Yeah, because I integrate out this high energy degrees of freedom, so the running coupling constant becomes smaller and smaller and smaller. And at very low energies, large distances, you can forget about this altogether. Yeah. What I defined for you was, so L is a scale, yeah? So, yeah, but so L is essentially just integral dl, yeah? Yeah, so DL was, exactly, but so the idea now is, so I've done for you one step, yeah? But the idea is, of course, you can repeat this many, many times. So this is the idea behind RG. So, exactly. I mean, of course it is, but this is like when you do an integral, right? I mean, so you do many, many small steps, and you get a Riemann sum. This tells you what the integral is. So here I told you what's an infinitesimal RG step, but if I can concatenate them now, I can do many, many, many of them. And you see what I have here, if you wish. So instead of dl, you could call this delta L, yeah, and this then would give you a lambda prime, would tell you how lambda changes under some small finite delta L. But now I just take the limit delta L goes to 0, so then I get a differential equation. So that's all I do here. Yeah, so in other words, this one I simply get from lambda prime equals lambda plus delta L or dl 2 minus beta squared over 4 pi. Yeah, and now I take lambda prime minus lambda divided by delta L, it gives me this differential equation. Yeah. Yeah. Okay, so ask me afterwards. Yeah. So okay, so this is the one regime, and the other regime is when beta squared is less than 8 pi. So then what you see is, according to the differential equation, so the coupling constant actually grows. Yeah. Grows with L. So that's a relevant perturbation. Okay. And so relevant perturbations, so they change the physics. So we started with this Gaussian theory, so just the free boson in Euclidean space. But if I add a relevant perturbation, so cosine beta phi with beta squared less than 8 pi, physics changes completely. You develop a finite correlation length and a mass gap, and so on and so forth. So let's so in this regime, the perturbation generates a finite correlation length and which can be estimated as follows. So I can just integrate this first order differential equation. So I get lambda of L is lambda of 0 e to the 2 minus beta squared over 4 pi L. Okay? And now if beta squared is less than 8 pi, so this grows under renormalization. And then at some point, even if I start with a very small initial coupling constant, this running coupling constants will become 1, order 1. Okay, but when it becomes order 1, of course the premise of my calculation no longer holds because I was expanding everything using that lambda was small. Yeah, but this coupling constant gets renormalized, and when it becomes order 1, surely my assumptions break down. Okay, and something else happens. Okay, so until when do I have actually? I have 25 minutes, yeah, okay. That will be fine. So, let lambda of L naught equals 1. Yeah, so L naught I simply call the value of L where lambda of L naught becomes 1 according to this equation, right? So here the approach breaks down as lambda is order 1. So this corresponds to an inverse length, the cutoff, yeah, which is inverse length, times this factor e to the L naught, which tells us how far we have gone along the flow, tells us how far we have gone in integrating out fast degrees of freedom. Okay, so this is an inverse length scale, yeah, and now, as I said, what happens if you have a relevant perturbation? The theory ceases to be critical, so you no longer have power law correlation, so you generate a finite correlation length. Now the inverse of this is a length scale, yeah, so this is a length scale that tells me where my procedure, where this relevant perturbation has become very large, yeah. So now you just say, okay, so we equate this with a correlation length, yeah, so my correlation length, or the inverse correlation length, is lambda e to the L naught, or we estimate it like this. This is lambda e times lambda of 0 e to the 1 over 2 minus beta squared over 4 pi. Okay, and so this is a very simple estimate you can make, but it's actually not a bad estimate. Yeah, yeah, it better have a dimension because xi has a dimension. So xi inverse has the dimension of 1 over meter. Lambda has a dimension of 1 over meter. We put lambda equal to 1. So there are many different lambdas, yeah? So my notations could be improved by using additional letters of the Greek alphabet. I grant you that, okay? Or the old German alphabet, actually. So this is a little lambda. This is dimensionless. Yeah, okay, so I was a little bit careless here. So what I supposedly should do is extract a dimensionless coupling constant, which is what implicitly I used. So I should put some dimensionful factor in my interacting part of the action. So I don't know. So let's see, I probably need something like lambda divided by a naught squared integral dx d squared x cosine beta phi lambda of x. That's probably what I should have done. Sorry? So then here you need this also. No, so just a moment. So no, this is correct. This is correct, yeah. So I should have stuck it there. right? So I was implicitly using lambda as a dimensionless coupling constant, but you're right, in order to compensate, I need to have this factor. You're happy with that? Sorry? A bit more happy. So which part are you unhappy? Because now, once I do that, so lambda is dimensionless. So yes, it's a short distance cutoff, if you wish. I mean, because obviously I have to put something here that compensates the dimensions of the dx squared. Yeah, and just put a short distance cutoff there. Okay? Yeah. Thanks for pointing that out. Sorry? Yeah. Okay. So the argument is like so. There is a length scale, yeah, or inverse length scale, which tells me when the dimensionless coupling constant becomes order 1. Yeah, when the dimensionless coupling constant becomes order 1, this perturbation has a huge effect. Yeah, and the physics changes. Yeah, so I'm no longer in this critical regime, etc., etc. And what the perturbation does, that we know, so it makes a finite correlation length. So that sets a length scale. It's the only length scale in the problem other than the short distance cutoff, let's say A naught. Yeah? The argument basically just says this inverse length scale, yeah, which gets generated under RG, we set equal to the inverse correlation length, which is the effect the relevant perturbation has. So this argument is basically just based on dimensional analysis, if you wish. Yeah, so RG tells you there is a length scale, a new length scale in the problem, which gets generated. And physically, there's a new length scale in the problem that gets generated, which is a finite, well, the inverse correlation length, and you set them equal. That's it. Yeah, so it's a very crude estimate, but it's not bad. Yeah. So the point is, if you deal with the kind of problem that we're interested in, some lattice model or something like this, your initial cutoff actually will be the lattice spacing. Yeah. So, and what this formula then tells you, the ratio of the correlation length to the lattice spacing equals this thing. So it's actually useful. Yeah. But a priori, you're right. It looks completely arbitrary here, but yeah. Okay. Other comments? So we have the length scale. So we have that. So far so good. Now. Yeah, so I skipped that. So now let's do the second order. And KT transition. Okay, so here what we have to calculate is the average of S int squared minus the average of S int squared. Okay, so you can write this out, yeah, which I'm not going to do explicitly, but what you get after one step or so is something like this: 1 over beta squared over 2 pi dl integral d squared x1 d squared x2 cosine beta phi. Well, maybe I should have filled in a... Okay, so let's see. Okay, so now I'm running a little bit out of time, space. I mean, plus beta squared h of x1, h of x2 minus 1. Okay, so this is what we get after a little bit of calculation. So let me briefly sketch for you the intermediate step, because maybe it's difficult to see otherwise. So what we start with is cosine beta, let's call it phi 1 plus h1, cosine beta phi 2 plus h2. So this is the average I would get when I calculate s squared. Yeah, and phi 1 would be now phi of x1, h1 would be h of x1, and so on and so forth. It's just a little shorthand notation. Right? So this is the kind of average I have to compute when I compute the average of s int squared. So now you just expand this. So this gives you e to the I beta h1 plus h2, e to the I beta phi 1 plus phi 2. And then we have plus e to the I beta h1 minus h2, e to the I beta phi 1 minus phi 2. So I just expand all the cosines and I multiply. That's all I'm doing. And then I have plus complex conjugate. Yeah, so that should be clear. Yeah, so I literally write the cosines as sums of complex exponentials and I multiply out. I get this. Okay, and now I use that the e to the I beta h1 plus minus h2. Yeah, I can again expand it to all orders and then re-exponentiate. So this becomes e to the minus beta squared over 2 h1 plus minus h2 squared. Yeah, so this is what you get by expanding and then re-exponentiating. And this now has several contributions. So I get something like e to the minus beta squared over 2 h1 squared and e to the minus beta squared over 2 h2 squared, which we already computed earlier when we did the first order. And then I get the cross terms, which is something new. It's e to the I beta h1 h2. Yeah, so then the terms we have calculated before, the h1 squared and h2 squared, that just gives us this factor 1 minus beta squared over 4 pi dl. But I have two of them, so I have to square this. And then I get e to the minus plus beta squared h1 h2. Okay, and now when I square this, dl is infinitesimal, so this gives me 1 minus beta squared over 2 pi, which is what I have written here. Yeah, so this is what I have written here. Yeah, and here. And then the minus 1 in both of these factors comes from the average of S int squared. Yeah, because what I have written on this other blackboard there is just S squared int H gives rise to all of this. Yeah? Okay, so that gives what I had written here. And now I'm gonna, where am I? Here. So we have this. Now, the new thing we have to work out is h of x1, h of x2, h. Yeah, and again, we can easily work this out from the modes, yeah, the high momentum modes. And this will become some function of x1 minus x2 dl plus order dl squared. And for the sharp cutoff scheme that we have applied here, what this actually is d squared k, and then we have lambda prime less than k less than lambda, e to the I k x1 minus x2 divided by k squared. Yeah? And you can just take this integral in polar coordinates. So this becomes integral lambda prime to lambda dk divided by 2 pi k, integral 0 to 2 pi d phi, e to the I k x1 minus x2 cosine phi. Yeah, and then those of you who like special functions will recognize this as a Bessel function, so I don't expect anybody knows any longer what this is. So it's a particular special function. Okay, so this is what comes out of the calculation. Now, so this would basically tell us what to put here. Now, this is bad news. Now, where am I? Yeah, just a sec. I need to know where I am. Yes. So what I'm using is 1 minus beta squared over 4 pi. dl squared is 1 minus beta squared over 2 pi dl, because dl is infinitesimal, yeah? So I use that. So I'm going very fast, I realize this, but if I don't go very fast, yeah, I don't get anywhere. So now, why is this bad news? So now, if you know Bessel function, so you know that this Bessel function actually decays very slowly at infinity. It just goes down like 1 over square root of the argument. Which tells us this is not a very localized function, which is a problem for the entire approach, which will become clear in a moment. But this has its origin in the fact that we're working with this sharp momentum cutoff. Yeah, and we're working with a sharp momentum cutoff because conceptually, then the steps of this RG procedure were maximally simple, because you really could integrate out these momentum shells in an elementary fashion. So this is an artifact of sharp cutoff procedure. So what we are working with here, so here is K, and we basically have this sharp cutoff, yeah? And because we introduce this sharp cutoff, this function here has a very long, slowly decaying tail. And so somehow, if we instead would reformulate everything, which I'm not going to do because it becomes more complicated, with a smooth momentum cutoff, you would get a result like this, like we have here, but with a function here, which is not a Bessel function, but something that decays exponentially at large separations. And that's what we want. Yeah. So, as I said, I'm not going to repeat all of this because I don't have the time to do this. So this would be a smooth cutoff, would be makes f of x short-ranged. Okay, and that's really what we would like, and we will utilize now. So Vincenzo, do I have 5 minutes, or how much time do I have left? Oh, okay. So I will try to do 2 and then stop. Yeah, I will try to do. Okay, so if I will use now that if I were to introduce a smooth cutoff, this function f would become short range, and then I would have e to the plus or minus beta squared h1 h2 minus 1. That would become beta squared f of x1 minus x2 dl is short-ranged. And then we can introduce center of mass coordinates. So r is x1 plus x2 over 2, and little r is x1 minus x2. And we can use this to simplify our cosines. Phi lambda prime of x1 plus phi lambda prime of x2. So now I use that these cosines, this one here, is multiplied by this bracket, which I just argued is a very short-ranged function. So it means it vanishes essentially unless x1 and x2 are very close. Okay? And when x1 and x2 are very close, then this relative coordinate is small. And now I just Taylor expand this. Yeah? So I Taylor expand this for x1 is approximately equal to x2. And I can do that because when x1 is not close to x2, this function here basically is just 0. So I don't get a contribution. So then I get here, this is cosine r dot grad r phi lambda prime of r. And so this is approximately, beta 1 minus beta squared over 2 r dot grad r phi lambda prime of r squared. And then the other one, phi lambda prime of x1 minus phi lambda prime of x2. So when x1 is approximately equal to x2, this becomes cosine, sorry, this was minus, and this is plus 2 beta phi lambda prime of r. Okay, so now we are almost done. Okay, so I use 1 minute. Yeah. So what we see is, to second order in this RG procedure, we now generated a new interaction term in our action, because we started with this perturbation cosine beta phi, but the calculation I've just sketched for you shows you generate what's called a second harmonic. You generate a cosine 2 beta phi. Okay? But now we're going to use what we learned from the first order, yeah, which is that if beta squared is larger than 2 pi, then this one will be an irrelevant perturbation, so to speak. So even though it gets generated, we don't have to worry about it. Yeah, so this will be irrelevant if 2 beta squared is larger than 8 pi. And I will simply assume that beta squared fulfills this equation. Okay, and then the other term I generate is now just a grad phi squared term. So it's a term that renormalizes the Gaussian part of the action. Okay, and that's the last thing I'm going to write down, and then I'm going to stop and carry on tomorrow. So the outcome of this calculation is s squared int minus s int squared is some non-universal. Okay, so here I still have to do some integral over the relative coordinate of this f function, which gives me some number, some non-universal number, which I call a. So this will be minus a beta squared over 4 pi squared dl integral d squared r grad r phi squared. And what we're going to do tomorrow, we basically will see what this contribution does to the RG flow. Yeah, so it changes the RG flow, makes it more interesting, and gives us a very interesting phase transition. But I'm run out of time, so I stop here. Okay.